Hello everyone, and thank you for joining us on another session of the NanoSurf AFM Master Class. Today we will cover session 3 with Dr. Patrick Fredericks. Patrick is the head of applications and service at NanoSurf and has more than 20 years of AFM experience. The session today will cover phase imaging, and if you have any questions, please post it in the chat, and at the end we will try to answer as many as possible. And without further ado, I hand over to Patrick to proceed with his presentation. So Patrick, it's all yours.
Thank you very much, Hector. Then let's get started. So let's hide the webcams. So also from my side, welcome to the AFM Master Class. Where is my now? Session 3 today, phase for material contrast. And yeah, let's get started with it. Phase contrast belongs to the dynamic mode, or in other brands also called tapping mode, intermittent contact mode, in principle non-contact mode. You can also count to it. So in a dynamic mode, in contrast to static mode, you oscillate the cantilever. And as the cantilever is bending downwards at the lowest point of the oscillation, it will slightly touch the surface. Like with the bungee here, it's the meaning that he will just touch the water. Once the tip is touching the surface, there is the spring from the cantilever having a restoring force and pulling the cantilever back from its lowest point. So that is the basic behind phase contrast. And what you do with phase contrast is that you excite the cantilever, and in this drawing it is with a shaker piezo. That's not the only possibility, but here it's drawn as a shaker piezo that brings the cantilever into oscillation. This oscillation you can detect, and in this detected oscillation you do not only get the amplitude, but you also get the phase delay with respect to the excitation. And this phase delay is the subject of today's presentation. To get a bit more background there, we are working now at the resonance frequency in phase. And how can one describe that? The cantilever can be described as a damped spring, a simple harmonic oscillator. And if you apply an external oscillation, the cantilever will start to swing at this frequency, a so-called forced oscillation. Sweeping the frequency and looking at the amplitude, you will see that the amplitude is not the same for every frequency. At the resonance frequency, you will get an increase in amplitude. And along with this increase in amplitude, you will have a phase delay. If you're very far below the resonance frequency, the cantilever will move exactly in phase with your oscillation, with your excitation. If you're very far above the resonance, it will actually go in counter phase, and at the resonance frequency, you will have a 90 degrees phase shift. Just for the understanding, at NanoSurf, we define the phase lag to be negative. So I know there is also opposite definitions with other vendors that say the phase lag is a positive quantity, but in NanoSurf, the phase goes in principle from 0 to minus 180. And we subtract a reference phase to keep it at 0 at the excitation frequency. Now what happens if I bring this cantilever close to a surface? Then we see that the free movement of the cantilever is obstructed. Obviously, the cantilever cannot just go into the sample. Now the question is, what happens with this movement? And there is two possibilities. Either it can be truncated, that the cantilever at the top part above, it does the same, but at the lower part, it just flattens off. Or you can actually get a reduction in amplitude. What happens actually depends on the frequency with which you oscillate the cantilever. If you're working below the resonance frequency, you will get a truncated amplitude as shown here on the left. That's, for example, what we have with wave mode. Here on the right, you see the case for resonance. At resonance, you don't get a real truncation of the amplitude, you rather get a decrease in amplitude. And if we try to describe that, that will also give us then the physical background why we can get a phase contrast. So as said, the cantilever can be described as a simple harmonic oscillator, and in a linearized way, you can describe the oscillation with this equation. The force working on the tip is dependent on the forced excitation, then on the deflection of the cantilever, the position, the d, multiplied with the spring constant, the viscosity or the drag multiplied with the speed, and then the mass multiplied with acceleration. Far away from the surface, you have there the spring, only the spring constant of the cantilever and the damping from the medium. But once you're getting very close to the surface starts to interact with the tip, and you can describe this in a linearized way by adding a spring constant for the tip sample interaction and a damping factor for the tip sample interaction. And the solution of this is a sine function with an amplitude A moving at the same frequency as the excitation, but having a phase delay. If you work this out, you can get a resonance frequency, which depends on the total spring constant and the effective mass. And you get a so-called quality factor, which is the ratio between the stored energy in the cantilever and, and the energy loss per oscillation. This is also equal to the resonance frequency divided by the full width half max of the oscillation peak. Now the left is of course difficult to measure. How much energy do I store in a cantilever during excitation, but these two values we can easily measure, and that it depends on the spring constant, the mass, and on the damping. And of course, for an oscillation, it is important that the total spring constant is larger than 0. If this is smaller than 0, you see you get an imaginary number for the resonance frequency. The amplitude depends on the frequency, and here you see the equation. There depends on the resonance frequency and on the damping. And the phase also depends on resonance frequency and damping as well. If the frequency is very low, very much lower than the resonance, the cantilever is moving without phase delay. You'll see that this will go to 0. At resonance, this goes to infinity, and you have the 90 degrees phase lag. And well above the resonance frequency, you get the opposite phase. You get there that the arctangent becomes 180 degrees or minus 180 degrees. So this is the graph as I showed you that belongs to that. Now, how do we, the KL, that's something we can calibrate. That's going to be dealt with in one of the other sessions. But what do we do with the tip sample interaction? Now, here you see descriptive, the cantilever, the force working on the cantilever, where you have there the force by the, if the cantilever is bending up, you have a force pushing the cantilever down to the equilibrium, and below it's getting pushed there. If you get so far away, you only have your force from the cantilever pulling it, restoring the cantilever to its center position. But if I'm at the bottom side, several things can happen. Now if I'm close but not very close, I can be in the so-called attractive regime. In the attractive regime, when the cantilever is at its lowest position, the cantilever itself will try to pull itself back to the center position, but the sample is actually pulling in the opposite direction at the cantilever. It wants to pull it away. Now, since this is working against the spring constant, we call that a negative tip sample spring constant, a negative TS. If we put that in the equation we had for the resonance frequency, you see KL plus KTS, but if KTS is negative, the resonance frequency is dropping. So if I get close to the surface in the attractive regime, you see that the resonance frequency is going to a lower value. As a result here, the amplitude drops if I started at the top. But what's interesting now for today is that at every excitation frequency that I would choose, the phase of the black curve is lower than that of the blue curve. So that is the case for the attractive regime. In the repulsive regime, something similar is happening, or you can describe it in a similar way. At the top, you have the force pulling down. But now at the tip side, the force, the cantilever force pushes it back to the center, but also the sample is pushing the cantilever upwards. So back to the center, actually adding to the force by the spring constant, giving a positive net spring constant. If I put this again in this equation, now KTS is positive, so I add two positive values. The KTS of the total K is getting bigger, and my resonance frequency is increasing. So you see that here the black curve has moved to the right. And now you see that for every excitation frequency, the phase is actually increasing. So you see if the resonance frequency of the interaction is changing, you will see automatically a phase contrast. During imaging, this will happen automatically. If my sample gets higher, shortly the amplitude will drop. And when the amplitude drops, it means that the resonance frequency has shifted, and that has a phase shift, also results in a phase shift, until the feedback loop has restored the amplitude and you're back at your original. So topography always comes also into the phase image. Now a little bit practical, how are we setting it up? For tapping mode or for phase contrast mode, you look where the resonance frequency is of your cantilever. You set that to your desired value. So here we took an amplitude of 500 millivolts. And for phase contrast, it is best to be in that repulsive side. In the repulsive side, there at the bottom side, you really sense the sample. And the attractive regime, you don't sense the mechanical properties of the sample so much, so you don't get a lot of contrast there. So you go on the left side of the peak. You can decide how far you want to go below it. Can be 20%. You can also stay closer to the peak, 5%. And there you try to keep that, during imaging, you try to keep that voltage constant. So what does that now happen with the phase and the during attractive and repulsive? I already said in the repulsive you get the best contrast. Here you see an example, a polymer blend, the topography in the top, on the left attractive, on the right repulsive. So that was on the left side of the resonance peak, and this on the right side of the resonance peak. And you see there is only very little phase contrast there, whereas here you have much more phase contrast, and they are both scaled to about 3 degrees of phase range. So you can really directly compare the phase contrast of the two images. So important, try to be on the repulsive side to sense it. Now in the ideal case, the amplitude feedback tries to keep the tip sample spring constant constant. That means that the resonance frequency would be constant and that the phase is mainly governed by the damping factor or the quality factor Q. And the Q variations are then dominated by dissipations via the local tip sample interaction. However, in reality, KTS may or will locally vary as well, with the result that the resonance frequency is also changing, that your amplitude is changing, and that phase that you see is not only depending on the damping. And that makes phase imaging very difficult to interpret. It gives you very nice images, but the interpretation and quantification of the images is very difficult. And here I try to illustrate that by an example. If you have the blue curve is an interaction with the tip, now I come on a different area where I have a larger damping. The peak gets wider. It's easier if I just would have drawn it wider and have kept the same height. I would have seen there the black curve would have become flatter and I would get a phase reduction. However, if I get a lower quality factor, I get less amplification by the quality factor, so my amplitude will drop a bit. The feedback will try to keep the amplitude at its set point, so it will move the cantilever a little bit up or down to again get the right amplitude, the set point amplitude at the excitation frequency, which means that the resonance frequency of your curve might actually move a little bit. And that will then also affect how much phase reduction you get there. So as you can see, the tip sample interaction results in the changes in energy dissipation, free amplitude, the relative set point, the absolute set point, if that is here about 250 millivolts, that will stay the same. But in relation to the free amplitude, it changes. Your topography might actually be influenced by that. That's a very small contribution. So only on very small, on very flat samples, you might see an effect of it. Otherwise, it will probably disappear in the general accuracy. And your resonance frequency of the cantilever will change. And what we are interested in, eventually the phase will change. Another reason to go for the left side of the peak is that sometimes you can have so-called phase jumps. As you can see, for each excitation frequencies, there is actually two harmonic oscillator curves that cross there at the same amplitude and frequency. One is on the left and one is on the right side of the excitation frequency. And sometimes this can actually jump between one and the other. If that happens, as you can see in the lower curve, you get a huge phase shift. This can readily happen if you start here on the black curve, if you start on the right side and you come to a topography to a high step. The high step might have sufficient force to push the cantilever into the repulsive regime and get to the other side. It is locally stable there until perhaps you have a step down again, And then you may jump back from the green curve to the black curve, getting the phase jump back. Gives you a fantastic phase contrast in the image, but sometimes it looks a bit stripy. And it's most of the time not the kind of phase contrast that you want, because it's not really a material property. It's just a coincidence from the topography feedback. Now let's give a few examples. This is an example of a polymer blend, polystyrene mixed with polybutadiene. That's the topography. You already see there is different islands there. On the left it's higher. There is some holes, or more or less holes in the membrane. And if I look at the phase image of this, you get a very beautiful difference between the two materials. Having one phase for the polystyrene and a clearly different phase for the polybutadiene. This was measured on the NIO AFM with a soft tapping mode cantilever. And what you can do with Gwydion or other programs, you can actually overlay the phase over the topography and you get an image like this. Now, what belongs to what? So here we see a different image again of the same mixture, and we try to compare data with force spectroscopy. The polystyrene is relatively hard, gives you a curve like this. The polybutadiene is a bit softer, gives you a less steep contact slope, and gives you also a different adhesion, force and adhesion work. And these things both will affect the phase contrast that you get. Now we have done a force map on this sample, and we have done also phase contrast imaging. Now here on the left, you see the phase contrast. The blue is now on the polystyrene, the red on the polybutadiene, and there you see the corresponding stiffness and the corresponding adhesion, and you see that both are different. Which of the two contributes now in the end to the phase contrast? That is the very tricky question. In air, most likely adhesion has most influence. A few other examples. Here you see a Silgard sample. It's also a polymer sample. Topography looks quite nice. You see there's the surface, there is some particles on it. This is not the typical Silgard image that you often see with nice polymer strings moving in. But nevertheless, it's quite a nice image. But if you now look at the face, you start to see additional information. So you see these particles there, they have a different phase compared to the background. And what's very interesting is you start to see here dark lines in the phase, and these dark lines, this directionality of the sample, you don't see in the topography. Once you know it, you can see, yeah, okay, perhaps there is something there, but it's not so obvious if you haven't seen the phase image. So here you see the phase image clearly gives you some additional information on the sample. It doesn't give me the Young's modulus, it doesn't give me how much adhesion I have, but it gives you additional information on the sample structure. Another sample here, it's a metal composite. It's a thin film, mixture of different metals. It's quite a rough sample. The roughness is about more than 60 nanometers. And here the phase image that belongs to it. And what you see there is some dark spots, and perhaps in the topography one didn't really notice them yet. But once you see them in the phase, you know where to look in the the topography, and then you see, hey, there is some debris on the surface. So it helps you to additionally get some information on your sample. Yes, there is 2 small particles. Is that just the same material? Likely not, because they have a different phase. Also there is some particles that are darker. What you here in this sample also nicely see, the phase information contains a lot of topographical information. So all these lines, that's not because there is a different tip sample interaction. There is here, there is just a different topography, and the feedback, because the feedback is there, you also have there a phase contrast. Whether this slightly brighter yellow is significant with this, that's a good question. It could be some damping, but it could also be saying something about sample differences. Phase contrast in liquid. With a piezo excitation, you excite the complete cantilever and you get a very messy spectrum, as we will see in the next slide. That's why we have on our newest instrument, on the drive AFM, we have photothermal excitation. With photothermal excitation, you have a laser beam with varying intensity at the base of the cantilever. That heats up the cantilever, and the cantilever bends because of that. I can do that at high frequencies, even over megahertz ranges. And that means I can also do it at the resonance frequency of the cantilever, making the cantilever oscillate. In air, that is very stable, but particularly in liquid, it makes a very large difference. And here you see the piezo excitation of a cantilever in liquid, and you see there is a lot of peaks there. And at every peak, you also have a phase transition. So also the phase is not very clean. It's a very sharp phase, but it's not very clean. If you compare that with photothermal excitation, there you nicely get the harmonic oscillator. There is some 1 over F. There you get your amplification by the quality factor. And there you have a very clean phase shift over the resonance. So that means you get, with photothermal excitation, you can get a cleaner phase contrast than with piezo excitation. Does that mean that you cannot use piezo excitation? No, not at all. I mean, we have done several experiments also with flex AFM, core AFM, that doesn't have the photothermal excitation, which gives you very nice images. What is important there is don't look for the highest, sharpest peak, but try to look for a bit of a wider peak where you have a nice a wider phase transition range. Then you will have a chance that you get a nice phase contrast. An example of that with a piezo excitation is here. This is an electrochemical experiment. So it's a gold surface where we can apply a voltage to. And if we apply a negative voltage to the gold, then we can deposit copper on it. The copper is as copper 2+ ions in the solution, and at negative voltage it can become metallic copper. That's the reference image. There is some acoustics there. Apparently I was talking too much during this experiment. And here in the second image, it started from the top. And there we applied the negative potential, and suddenly you see that the topography is changing. And this is not really the topography directly, it's actually the derived topography. And you see there that the structure has changed. That's because of the copper. If I afterwards apply a positive voltage, I can reoxidize the copper and I get back to my gold surface that I had before. So that's topography, but this is about phase. And in phase, you actually nicely see a contrast. Yes, particularly in the left, you see again the acoustics. but you also see the topography. If there are edges, you see that in the phase contrast. But interestingly, the moment that the copper is on copper, I have a different phase delay compared to the gold. Is that a coincidence? No, that's why we also did the dissolution of the copper. This is nicely reversible. So the phase nicely goes down again if I dissolute my copper and get back to my gold surface. So as you can see, the phase contrast you can do in air, you can do in liquid. For polymers, it's nice. For detecting material on a surface is nice. And one of the most applied applications for phase contrast is actually magnetic force microscopy. I will not go into detail on that. I just show you 3 nice images. This is on a magnetic tape, on a permalloy, and here on artificial ice that are measured by the phase. So here the cantilever is not allowed to be in contact with the surface, otherwise the topography induces more phase contrast than you get from the magnetical forces. But if the magnetical force between the sample and the tip changes, depending on where you are, and if the force changes, becomes more attractive or more repulsive, you'll get a phase shift, and this phase shift you detect as an MFM signal. With that, I'm getting to the end of this presentation. I hope I could convince you that with phase imaging, you can show contrast that's caused by the tip-sample interaction. It's related to either shifts in the resonance frequency or changes in energy dissipation. And this tip-sample interaction depends on topography. If I go over an edge, I will get phase contrast. If there is adhesion, you will get phase contrast, elasticity, but also magnetic or electrostatic interaction will cause you a phase contrast. Not for the magnetic and electrostatic, but for the other ones, phase contrast is generally performed in the repulsive regime. There you will get the largest contrast caused by the sample properties. The phase contrast can give you information that is not visible in the topography, like those lines that we saw on the Silgard sample. And the phase, important to realize, is that the phase information is not quantitative. You don't get the Young's modulus out. You don't get the adhesion force out of it. It's a qualitative measurement, and the contributions are often entangled. So you do have the topography in, you do have adhesion in, you do have elasticity in, though in air, often the adhesion is dominant, and in liquid, where you already have a very large damping by the liquid itself, the elasticity is getting more important. And this, of course, that also means that phase imaging you can do both in air or liquid, or even in vacuum, but that's that was not discussed in this presentation. So with this, I would like to conclude my presentation. Already going for the before going to the questions. The next time will be an overview of electrical mode by Dennis and Hector. Oh, sorry, there is a small typo there. And then in the new year, we start with Dalia on image processing, and then continues with the other sessions later. I would like to thank you for your attention, and then we get to the question and answering session.